models that can live, for instance, on your watch or on your phone. And that's the part that we're going to talk about. So how can you build a very, very small, like kilobytes model that is as accurate as those that live on the cloud? Super challenging problem. So, oh, I cannot change slides. Oh, perfect. So there are 4 core components that you should think about it. As I say, the latest is user privacy. So big tech corporations, right, constantly get scrutinized, how they collect data, how they use the data. And users like myself and like you, we want to know, well, what is our data used for? So when you build models that live entirely on your phone, they don't need to live to go to cloud, right? And the user can feel more secure. Number 2, we have actually a problem with connectivity, right? We love using our features and we have access to 3G networks and 5G and whatnot, but not the whole world actually is fortunate to do that. And even for our case, right, if you go on a hike or if you go through a tunnel, you still cannot execute many of those commands, especially if you like smart features in your assistants, right? And having these models on device, actually, they don't need to interact with server-side applications, right? Because they directly execute on your phone. Third, but also very important, is now we have a lot of efficient computing. So take a look at all big tech is creating customized chips, right? Silicon chips. And we should just take advantage of that, right? They're now more efficient. They're very fast. That means our neural models can work and live on the devices. And last but not least is consistent experiences, right? So as a user who uses applications from big tech, sometimes you wonder, wow, I execute or I say the same command twice, but I get different results, like what's happening? So if you actually have your models on device, we're going to make sure that every time the experience is preserved, right? So these are the 4 important blocks that stem the whole question of why should one work for on device? And here's an example. I cannot see the audience, but I am sure all of you use different assistants in one form or another. For instance, I have all of the different assistants, whether it's Google, whether it's Alexa, smartwatches, phones, and you just, I don't know, use them all the time for anything you do in the house, right? So let's take a very simple experience. You enter in your house and you say, turn on my living room light, right? That's a typical conversational AI problem. And I'm going to highlight how does it work, and maybe that will help you understand. So we say a vocal command, right? Turn on my living room light. And typically the first model that gets evoked is the natural language understanding one. And it has 2 purposes. One is it has to understand what is the command. We call them intents that the user wants to be executed, and which kind of entity should be populated, and we call them slots. For instance, the model should understand that we have a device like light, and we are requesting something in location called living room, and we want for the device and for that location the intent of turning on lights to be true. And that's the most important part, right? Because if your natural language understanding component doesn't work, then the rest of the system starts breaking down, and your conversational AI experiences will not be very good, right? So after natural language understanding comes a dialogue manager, and its part is to take all the intents and slots that were detected by the natural language understanding system, send them to the backend and understand well, one, do I have such devices? Can I execute the command? And once everything is checked, typically they send back, let's say, confirm the device is on or confirm the command is executed. And the output gets passed into the natural language generation component, who then knows that, okay, for this specific command, and I'm confirming that the device is on, I should produce an outcome such as your light is on. And you can think about it, we keep talking to our systems, we sometimes change the intents, or from turning on the light, we go to music. But these are kind of the 3 standard components that people have to focus on and make sure that language is properly understood so that we can move on, right? And most of the technology today happens actually on cloud, right? But if you objectively start thinking about it, well, we execute so many commands, right, per day with our devices that some of them actually could live directly on the device. So I turn my lights via voice commands every day, multiple times a day, right? But if you notice, there is a big lag between when you say turn on and by the time the light is on. And at some point you're like, wow, okay, I don't want to use my device anymore. I'm just going to open my app and I'm going to control it from there, right? So now the experience is getting broken. And the way to fix it is actually you can go and build fast on-device models that when you say your command, the model will just go understand it, execute it right away. And there's other applications. For instance, people who carry smartwatches, right? Yeah, you have seen that when you receive a message such as like, hey, how is it going? Right now, you have to go and type everything with your finger, and it's kind of like clunky experience, is not good. But actually, we can automatically generate responses for you. They will sit on your device, and then you decide what you pick, right? So these are pretty nice, pretty nifty applications. And there's many more, like you can think about translation, you can think about spam, you can think about anything you try to post. We can do all of these different applications for you at a snapshot. So it's important to think when you build such applications, actually it's super hard, right? First of all, you have lots of hardware constraints, right? Your phones have it, let's say 16 gigabytes, in some cases even low. So you can't sit down and build big, large NLP models, right? They'll never fit on your device and your computation will be slow. And if they fit on your device, well, they'll drain your memory and your battery, right? So they're not energy efficient. Then if you build such models and you make them small, biggest challenge is that they won't be accurate, right? So then people would not want to use them. That's the second challenge. Number three, maybe you built all of these models to be accurate and maybe they are not very bulky, but you cannot do complex tasks. All you can do is like a very simple, like, I don't know, binary prediction task, right? We actually want to make sure we support all different types of natural language applications, right? We call structure prediction things such like name entity extraction, such like slot extraction in what you saw in conversational AI. And we want them to be able to handle all kinds of large scale classes, right? If you think about it and you go to shop on Amazon or any website, you have thousands and thousands of categories in which your products are organized, right? So we want our models to be able to spit out and support like large output spaces. So we have plenty of challenges to worry about. And that's what it's make it very hard to make it work, but the needs are very high, right? So we took a look actually at what were the things that people did to solve this problem. And it's very funny because when we describe it to a couple of folks, they say, well, how is this a problem? You can just hash the input to the output category. You do this across all the examples you want and your problem is solved. So you guys have no problem, don't create problems. And I was like, well, good point, but you either are not an NLP expert and you haven't thought about the complexity of the problem, or you haven't built a real application that somebody can use, right? So here's an example. Even if you just want to say something very simple, like play a song, right? The vocabulary is so rich, right? There's multiple ways in which you can go and express the same thing. Sometimes you can use like play something by Madonna, or you can just say play a song by Madonna. And if you start thinking about all the different ways people say the same thing, that space will explode. So you cannot hash the whole language space for every single thing on earth and hope that this will solve the problem, right? So these kind of approaches actually do not work, right? And also if you hash every single thing on earth, your inference time will be like very like, how to say, it won't lead to the solution that you're looking for. So back in 2012, different people started thinking, what can we do? And they came up with fast sampling approaches, but that didn't solve the problem, right? Later in 2017 and 2018, others decided to do some of these like graph learning approximations, and maybe that can help alleviate some of the problems, right? But what was interesting is that their models were so huge that you can never fit them, let's say, on a watch, or you cannot put them on the phone, right? So maybe you can put them on a laptop, but not really on any of those devices. So at that time, like my colleague, like both of us were at Google, we were talking to each other and we were like, okay, can we do something better? So actually, Sujit left Google and he's doing like a startup in this space, right? And both of us, we talk to each other like, well, neural networks have shown to revolutionize all the NLP, right? Everyone uses them for any single approach, whether you want to do sentiment, whether you want to do like intent, any of these things, right? So we know that that's the right way to go, yes. But then how can we make them so small in size? So nobody knows, right? And how can we make them efficient? And at the same time, reach state-of-the-art performance. And so both of us said, okay, let's start thinking about different models and let's start trying. And when we shared this idea and initiative to people, they're like, well, I don't know if it's that going to work. Maybe you guys like, I don't know, you try it and it doesn't work, right? But we actually persisted. We started in 2018. And ever since, from 2019 until 2021, like we've made a lot of like progress and impact in that area. And here's what's interesting, like Sujit and I literally sat down and built a brand new paradigm and came up with these projection neural networks that can help solve a lot of the problems and challenges that I highlighted above, right? So all of our work is published, so you can take a look at it. And we made sure that we evaluate on open research data sets such that anyone can take a look at this, replicate results, right? Just like literally think about it. Imagine that you're someone who wants to solve a problem, right? And you come up with your data to us. You just say X, for instance, is my data. It could be tweets. And why I think about it is the label space. And you say on my tweets, I want you to detect sentiment, or on my tweets, detect hate speech. So you give us input this type of data to us, right? What we do is like we take it and we learn on the cloud via our projection models, right? Networks that are actually very, very small and compact, right? And I'll show you like how some of these networks look like. And then what's interesting is like once they're ready, we use TensorFlow Lite to actually take them and deploy them on any device. And this could be your phone, Android, iOS, it could be your smartwatch, it could be anything, right? So what's interesting is the way we design the networks, you can very quickly customize them, right? You can say, well, my application will run on a watch, so make the models like, I don't know, kilobytes. This is the kilobytes I want. Somebody else can say, well, my application runs on phone, I have more space, this is what we want, right? So we can customize based on your needs, right? But what's good about them is that they're very fast at inference, right? For those that wonder, like, what's inference is like, anytime we pass a new example, think about it, new tweet is coming up instantaneously, in milliseconds, we can predict like what's happening real time, right? And now I want to kind of like dive a little bit deeper into, let's say, one of the simplest networks, and I will leave you links to like more advanced versions, but let's start with the base, right? So the first network that we designed is called self-governing neural network. And it starts like that. So like any single NLP application, the inputs are the words, right? And here's an example. We have things like quick, brown, fox, jumps, right? After that, the first thing you do is like you actually extract features and you decide how you want to design those features. You can keep them very simple, like n-grams. You can do unigrams, which is single word, bigrams, trigrams. You can add them and make them skip grams, which means you skip over like certain words. Or actually, if you want, you can complicate life and include parsing, part of speech tagging. But definitely what you're not going to do is use word embeddings. So currently all cloud-based applications use a lot of the word embeddings, which are like gigabytes in size, right? If you use them, they'll never fit on your device. And that's where the trick is, right? It's like, how can you get rid of embeddings and make sure that these approaches work for your watch or for your phone? So you generate your feature space, and the most important part is to create fingerprints for those features, right? So think about them. Fingerprints are like literally we create for every string like a hash ID, which is an integer, right? And a weight. And the weight here is like we count how many times that string was seen in the upcoming text, right? And when you work with like simple text, like let's say tweets or like single sentences, news headlines, right? Typically, like your counts are like 1 or 2 because it's very rare to see a lot of words and very frequently, right? But when we do and take these networks and let's say we want to categorize books or we want to categorize long emails, right? Then your counts will start changing. So you go from the features into your sparse vectors, right? And then this is where the magic happens, right? So the goal for us is to go from these sparse vectors into a very compact binary projection vectors, right? And for the purpose, we use local sensitive hashing, right? It's very commonly used in industry when you want to map from very, very large spaces into small spaces and you want to do fast things like searching or something like that, right? And the way they work is like you start with a random seed vector, which actually has T by D, where T is the different number of functions that we use, and D is the dimension, right? And in our case, for instance, and it's variable, you can decide like we change with 1,120. And you take this random vector and you multiply it by the sparse vector. And literally, we do the dot product, right? And we see like, well, is the dot product larger than 0? If that's the case, in the binary vector, you will see like a 1. If that's not the case, right, and the product is lower than 0, then we put a 0. And you can think that this process is repeating for all the different T functions that we use, right? So when you repeat this process multiple times, you end up with a very compact binary vector that actually captures what the meaning of your quick brown fox jumps means, right? For people who want to know more about like how does locality sensitive hashing work, how does the projection functions look like, I encourage you to take a look. So Sujit has a couple of these like recorded talk from ICML. You can see the theory, you can see the proofs there, as well as like how some of these implementations happen, right? But in a gist, what you want to remember is like we go from these large, huge vectors into these little tiny binary vectors. And the goal is like we want to bring together similar phrases or similar sentences as close together as possible, right? So if we take the vectors and we actually take a look at like what's behind them, you're going to see that they kind of cluster and aggregate similar phrases like howdy, everything's going well, or hey, how is it going? And things like that's funny, right? Is sitting a little bit further away from that similarity space, right? So it's very, very interesting property. And that's exactly what allows us to get rid of embeddings. It allows us to create these compact networks that live on the device. It's very important, and I listed it on the site. Every time from input all the way to binary projections, everything happens dynamically. The whole generation happens on the fly. So you don't need to pre-store anything. Comes a sentence, quickly extract the features, quickly create a sparse vector, run the projection layer. And then once this process is done, we create a fully connected layer, right, a denser model, and we do softmax on top. Primarily in this case, softmax, because we are interested in multi-class classification problems, right? And this was like the first network that we actually designed. And what was super amazing is, well, nobody until that time knew actually how to produce such small, efficient networks that work so well, right? So that was like the first on-device neural network. The model is very intuitive. That's why I'm going with it. I want to make sure people understand it. And as I say, the most amazing property is like super fast, right? Which is what you need in real time. It's very efficient. You don't need to store anything, right? Everything happens on the fly from words all the way through projections, right? And we call them embedding free because you don't need to preload them. And it's super amazing. It transforms inputs, as you saw, into very semantically similar spaces. And the most important part is you're going to see how they work in real life in practice, right? So let me show you a couple of applications. And given the interest of the audience in conversational AI, like I'm showing examples that are related to that, right? So we took like an open source data set, switchboard dialogue act. And typically it has conversations between two people. One person says something, the other person replies, and the conversation keeps going. So the goal is—
Anita,
yeah.
sorry to interrupt, but I thought before moving on to the next topic, were there any questions about the previous topic so far. Good.
What part of the model is learned during the training? Like the fully connected layers, there are weights associated with that, and there are the functions that are learned on the fly. Right? So, what part of the training, what part of the model is learned during the training?
So everything you see here, right? That's like the whole training architecture. Think about it. If your input was tweets, yes, and your output was the sentiment, whether it's positive or negative, you're learning how to map input strings to those output classes, right? And the applications can be different. Here, for like interest of the audience in conversational AI, I pick examples exactly for this, right? You have input of a conversation, which is like something somebody says, and the output is sets of labels. And that's what I actually wanted to show on the slide. But you can learn anything, right? So any classification problem, you come and you say, I give you an Amazon review, predict how good the review is on a scale from 1 to 5, we can do that. You can say, here's a news article, tell me like, what is the category? Is it economy? Is it finance? Is it someone else, right? So the goal is, as long as you have input data with output labels, right? And it's a multi-class classification problem, you can use that architecture to actually learn those, to solve that problem, right? And that was the part that I wanted to come to. So if you have those networks, these are examples of tasks, and think about it, you can do any task as long as it's a classification task, right? But that's the input, right? The input is you have a person that says about 12 foot in diameter, and the task here is you have to detect that somebody is making a statement. So in conversational AI, this kind of like labels help understand, like, should we evoke the computer or like the system to generate something to continue engagement? Is it a question? Like, what is it, right? We use the data that is open source by everyone. We did not create it, someone else created it. But the goal is, yes, given a conversation between people, can you predict, like you see these like boxes in red, can you predict like what is the class? So in the first case, it's a statement. Somebody says, oh yeah, that's like back channeling, like you're like supporting. Then the person is asking, like, you never think about that, do you? And we know that it's like a yes, no question. And the reason we do that is like, if you're building, let's say, a conversational system, or if you want to have like a smart reply, it's good to keep tracks so that we actually know like what things we should be predicting or inserting or completing, right? So here's the interesting aspect, right? In 2019, when we started working on those models and got our first results, like nobody was working in that area, right? Because most of the people worried about cloud applications, worried about, let's build these gigantic like GPT-3 style models, right? So when we created our network, well, it was a bit hard, like how do you compare it, right? I mean, we can simulate and do like different variations of the models, but that's not quite par to par, right? So we decided, though it's not fair, right, because we have constrained resources, to compare against prior solutions, right? So we took all the people that worked on this problem and on this data set, and we were like, let's see like how far do we go? And so think about traditional like naive-based models, right? And take that as a baseline, where somebody looks at the data, comes up with sets of features, uses the feature, trains the naive-based classifier, and then takes the prediction and evaluates the accuracy. How good was my model, right? So those models are like 47%. Then you can take like more of these like sequence, like HMN style algorithms, and you see like, okay, they slightly improve performance. And then we kept going, right? As the field kept evolving, you saw that in 2014, like everyone started moving from standard like classifiers and feature engineering into let's design our neural network, right? And you see that people use a lot of CNN features, which are like the very popular in computer vision, and kind of like people apply them to language as well. Others were trying to do RNN and all the attention papers, right? So these are like doing slightly better. And you can see different sets of variations of how people were literally creating yet the next neural network and trying to see how well we do on these models, right? So what was interesting is like we compared against all of those, and if you see, actually our performance is very high, right? It's like 83% accuracy. We work with a very small memory, and I'll show you like different configurations on the memory that we have available. And our models are super fast, by the way, blazingly fast compared to all that we see. We have super small memory footprint, super high accuracy, and that was our like, hey, this seems like exciting. Let's keep going and let's keep increasing complexity for that task, right? So then we decided to take different sets of data sets, right? A lot of these conversations that are between people, somebody recorded them, transcribed them. So now you have multiple parties. It's like more than one person talking. What's interesting is when you have different people speak, right? The language is a little bit different. When you have transcriptions, that means sometimes not everything is perfectly like written. So definitely there is challenge for our models, right? And also in this specific IC SI like data set, what's interesting is the topic is very different. It had a lot to do with like computer science, right? But the task is consistent. It's like given a sentence, predict like what is the dialogue act, right? And as I said, these data sets are publicly available and anyone at any time can replicate them. So if you see 4 people are talking, topic is kind of slightly shifting, language varies, it could be longer sentences, like smaller sentences, some are like saying, is this a suggestion, so on and so forth, right? And one of the reasons we actually picked this data set is because many of the people we noticed who worked on the previous data, they actually continued to also do similar progression, right? They wanted to also track like, well, if I increase the complexity of the text and the complexity of the interactions, what happens to my models, right? And we see similarly to before, like the naive Bayes models, they're kind of at the bottom, right? They do good, but they don't do great. Then we see like the neural network models, they're slightly starting to pick up and they're like having 10% boost. And then what's interesting actually is this graph. Like we see, wow, okay, our model is kind of comparable in performance to the RNN. We noticed that on the previous data set, the performance was different. So we actually wondered like what happened, what's the cause here? Like how did it currently like shift? Is it like due to something? And actually the authors of the paper were very kind and they said like, oh yeah, actually what we did is like we pre-trained the embeddings on additional data and that actually gave us extra boost. In our case, we don't do that. Whatever data is available for training, that's what we train on. We don't do any pre-training, additional like fine-tuning or adding more data, just like very objective, like same train, same test, right? But then when we compare the parameters of the models, right? The RNN model is like billions of parameters. That means huge size, right? And the model here that you see for 86.7 accuracy is like super tiny, right? It's 300 kilobytes. So it's kind of impressive, right? If you want to make sure these models work on device, definitely that's the way to go. Let me pause here, because then I want to show like different variation of the network and I want to make sure like if there are other questions then and if you understood the tasks and the data sets.
Yeah, thanks for pausing. I think we have a few questions.
First question is, so how do we go from the n-grams model to the projection? So what is the process to do that?
Yes. So remember, like this is the process, right? This is the process of how you go from quick brown fox all the way down to the output, right? And the projections is like layer, like over here, number 3, right? So as I said, you create your n-grams or skip grams or any features that you want, right? And then what you do is like you have to we call fingerprint, right? That means you go from a string to an integer and you create these large sparse vectors, right? And the way it happens is like, let's say to quick brown fox, you assign number 2132 312, right? And you have a weight. And as I said, the weight is the count, right? How often have you seen that string in your sentence? Right now the sentence is 4 words long, right? So it's like one time I saw it. Then to go from the sparse vector to the so-called projection vectors, right, we use the LSH, right? And that's the part where I said the magic happens, because you create these like random vectors, yes, with a seed, and you have two functions, different functions, right, by the dimensions, and you multiply that projection, that random vector by the sparse vector to create the projection vector, right? And so we repeat this process d times, right? So the idea is like from this long sparse vector that you see to end up with this small compact binary vector, right? That has just zeros and ones. So if you want to know more, as I said, two things. One is like at the end, I'll share like papers to our work. But also, if you just want to know, I really want to know one thing, and it's projections, which is totally fine, right? So there are talks on YouTube that you can watch by Sujit, and also you can read the paper, which is like focus just on that, just on the math behind it, how you do the inference, how you do the multiplications. And I think if you do both of these things, then your questions will be fully answered, and you can, re-implement like that part of the algorithms.
Another question?
Yeah.
Sure.
So how does the performance change as we increase the length of the sentence? Does it actually, is it comparable to the embedding models that we have, or?
Well, actually, it's a very good question. You know, remember 2018, nobody knows how to do that. First model with SGNN. By now we have like 10 different versions. One is, think about it, each version is better than the next one, right? When we first created these self-governing networks, because of the applications to conversational AI, blocking, let's say, hate speech and some of these like spam, like as people were typing, like, can you block it right away or say it's sensitive, right? We focus on short text. Later, which I'm not going to talk here, but I can send you material, we try to do that for long documents. And think about it by long documents, news articles, right? Or for example, snippets from books or snippets from Amazon reviews. If you take those models the way you see them right now, they don't work that well on large text, right? Typically, you have no problem. You can use as long text as you want. You take it, you can still hash it, you can still create the projection layer. But what won't work in terms of performance is if you use this neural architecture, right? Because if you see here, it's a fully connected layer with softmax. When you have longer documents, we want to capture many other things, the context around the words, for instance, like we want to do attention over all of those networks. We want to do many more things than what you see here, right? And I can share, like we have papers on that, and I'm happy to share, and you can take a look. But one thing before we shift context, what I wanted to say is like, here I'm showing you like, the easiest ones to digest, right, the networks. And I wanted to show for the class two different sets of applications. One is like if people want to do these multi-class problems. And after I talk about SGNN++, I want to talk about people that want to solve like the so-called structured prediction problems, like the entity extraction, right? And the core part is like the whole projection layer mechanism is the one that makes the whole, efficiency work on small devices.
Was there another question in the back somewhere, or?
I just answered.
Okay.
Great, awesome. And by the way, Adwait, similar to last year, I will share the two last slides have the papers. As I say, they're different from many years, and they're focused on different topics, but we have like different variations of network for short text, for long text, for sequence extraction. We actually did tests on attacking our own models to see how robust are they, and all kinds of stuff, right? So I can't cover everything, but I want to make sure that at least the intuition is there, and then everything is available these days online, so you can definitely follow up. But let me.
We had one more question, I think, from the front. Did you have a question?
Yeah, I was wondering if there's any benefit of word embeddings over the binary representation?
Well, how are you going to do that?
I mean, just in terms of like performance, because it seemed like the binary representation like worked just as well with like so many fewer parameters. Like, why would anyone use the word embedding?
Oh yeah, I see. Now I understand your question. I thought that you were trying to take the projection plus also add additional embeddings, and then the concern for me was going to be, well, how are you going to make those models compact? But actually, yes, the answer is, do you know, it's like, so just like you have the current, like all of birth models and so on, right, that are trained on large data, and you have these representations. Actually, what we did is like we train our own projection embeddings literally on large text, right? Everyone can get the 6100 data set and do that. And what you see is like, well, actually, I can start using my projection embedding, just get rid of all of these like other embeddings and make it work, right? And that's one of the parts that, as I say, it's like a key to making sure if you want to have like small models, that's the way to go, right? So yeah, very good question. And that's exactly what we did. So actually, do you know what? Great question, because we won a best paper award for exactly that this year at the beginning of the year at EACL. Yeah. Cool. So let me glance over, because I'm checking also the time. I want to make sure like we have time just to kind of show you how you can keep playing with this. Think about it. Once you take all the classes, you're not going to only learn like how to design these different networks and how to tweak like your embeddings. You will see like the space explodes, creativity is there. You truly enjoy it, right? So as I said, first when we started, we just like wanted to solve one thing, is like solve the problem, get it done, then wonder about how to further improve it, right? And version 2, which was like in early 2019, was, okay, we are language people, right? So by training, we love language, we understand language, how words interact with each other, word order changes across different languages. But in the first version, we just cared about like some of these like raw like words, right? It's like n-grams done. But one thing that is very interesting is in language, if you take a look, like there are a lot of these morphologically rich languages, right? So for instance, suffixes, prefixes, roots across languages give you a lot of this information. So for us, oftentimes in industry, you can't just build solution for one language, right? Maybe you start with it, but that's not where the process ends, right? People want you to expand to 100 languages very quickly. And then you start wondering, okay, so what can I do? You have languages with different properties. Some are more morphologically rich, others are not. And that was version 2, right? Our version 2 was SGNN++, which means like, well, it's very similar to SGNN, but we were thinking about, well, how do I capture two things, which is like one, the structure of the language, the structure of the words, and two is like the context, right? Because if you notice how even the current like word embeddings are trained, the context of a word is determined by the words surrounding it, right? So then we said, well, great. So maybe what we can do is we'll have a space that learns like, let's say, the word projection, and we'll have a separate space that actually can learn the character levels, right? So you still start with the same input, which is the words. But if you see in the graphs, like we have on the left side, like the word representations, and we're going to learn a projection space over the words, similar to what you saw. And we're going to do the same thing independently for the characters, right? So when we do that, we will capture both of these properties, right? And that's the so-called the structured projection, right? So we want to combine the word and the character. So each of these will go in parallel with their own like random seeds, but in the end we'll concatenate like the projected space, right? The layer. And part 2 is the so-called the context partition projection. So we want to make sure that when you take a look in the previous example, right, we always reserve the same space for unigrams, bigrams, trigrams, and so on and so forth. Here, what we decided to do is like based, like we know unigrams are more frequent than 5 grams, right? So we reserve different spaces for so-called feature type, right? So unigrams, as I said, more frequent or the most frequent, 5 grams or the larger the grams, like you don't have that many different variations, right? But when you do that, and you, let's say you reserve for the words and for the characters, but when you do that, right, before actually with the reserved space, sometimes things could collide, right? And when they collide, models can get confused in the prediction. So now when we actually reserve separate spaces, that actually helped us solve a couple of problems, right? We have separate space reserved for unigrams, for bigrams, that avoids like, let's say, collision of the features. Number two, when you start implementing, right, you can parallelize the processing for all of these things. And actually, later in different work, we use that strategy to actually learn the representation for different tasks, right? So the second variations, and as I said, like we got like very creative. We have like different model called Prosecco and Prada and so on. But you can get very creative in how you play with language and what you do and how it performs. Now, going back to the original task, here I want to highlight. So now at least we already had the baseline, right? The baseline is original version where you had like SGNN. And this one is the next generation version where you take words and characters when you're playing with the partitions, when you're playing with the with everything, right? And you see that consistently across both of these data sets. So our model is doing great. It's doing much better, right? So this is fantastic. Then we said, great, let's try different tasks, right? And there's a data set called ATIS, and people use it when they want to test how their dialogue system works on, let's say, flight-related data, right? So typically it has sentences like, how far is the Auckland airport from downtown? And people have to tell you that, well, the person is asking something about distance. Sometimes you have sentences like, how much is the price of a ticket from LX to SFO? And you know that you're asking for airfare, right? As I say, those labels, the intent labels, they're used such that the models know like what to predict, how to predict, what to return, right? So we use that data set, completely different from before. We've never evaluated on it. And we started seeing that our model actually consistently does better, right, across all the previous model. One interesting thing is like, sometimes we notice that people try to build joint models for intents and slots. And oftentimes that so-called slots, if you know that LA is a, let's say, location/airport, or SFO is location/airport, they take those labels, add them to the model, and kind of like boost joint performance. So we didn't do that. And without those additional tricks and information, actually the model keeps going great, right? So what's interesting, we, as I say, want to go and make sure this is working for different languages, right? It's really hard to find data set that, you know, is equivalent for all of these languages, and we can test as many things. But we got like a customer feedback data in like English, Japanese, French, and Spanish. And there the people are trying to automate what's a complaint. If it's a complaint from the user, send it for someone to immediately reply or for a call. If it's a comment, okay, maybe good to see, but maybe you won't do anything. If it's some bug on the website, maybe take an action, so on and so forth. So the beauty of this data, as I said, is the language diversity here, right? And that's what we wanted to test. If we take our models the way they are, we use the exact same procedure, we don't overcomplicate life, how fast can we go adapting to those languages? So the answer is pretty fast, right? But what's interesting is that performance is very different, right? So in general, if I take English and Japanese and French and Spanish, somehow the English data was like very different. And it is related also to the things people ask and how they ask. So it also depends on the people who collected the data, like what were I say, the diversity of the expressions that they were collecting, right? But we use the same data set just like anyone else. And we took a look at like different models that were implemented, right? So similarity baseline is like we saw that somebody was actually taking a sentence, yes, taking the words from the sentence, creating like frequency-based features, normalizing them, and just kind of trying to do the similarity between a sentence and a gold standard, and say like, oh, if my sentence is similar to this one and the label is, let's say, comment, then that's the label for my sentence. And that's what's called similarity baseline, right? So we see if you do something like that, well, your model does well, like 48% on English to 70 on Spanish, but definitely it needs some additional work, right, to make them better. So then we go and see like all the different people who do logistic regression. or use some of the pre-trained embeddings, by the way, which are widely open. Some people got very creative. They took the output of sentiment classifiers as a signal that maybe if it's negative, maybe that's more relevant to be a complaint versus a comment, right? And you have even people who were incorporating external knowledge bases, right? Knowledge base could be, let's say, a repository for someone who collected complaint words, right? So it's kind of like a lot of information that people use in hopes to get to solve this problem. Think about it in test time. Nobody knows what the data looks like, right? You have your model, like stream of sentences comes in, you make predictions, and then you run an eval script that tells you that's how well you did, right? Next, what was very interesting is our model was very similar, like in performance in terms of like the Planck multilingual approach. That was a system that actually participated in different challenges. And I think that was one of the challenges. But what we noticed is that the team working on creating the models were actually doing a lot of translation. And so they were using the translation from Japanese, French, and Spanish, and added it as data to English, and then repeating the same process for every language. And the reason to do that is to increase your training data, to increase the diversity of the vocabulary, right? And they were also using a lot of these like different multilingual embedding, a lot of part of speech tagging information. And this is all great. But remember, if you want to have part of speech tagging running on your phone, that means you have to build yet another model or figure out like how to do that in real time and be very fast. Same thing, if you want to use live machine translation, and just to get like this 2% improvement, it's not worth it, right? Because in research, nobody's time basing, right? Maybe your model can run a whole month just for a number, but in real life, no user will wait. Like imagine you search for something and it tells you come back in 1 hour. So that's not a good experience, right? Our purpose as always, make sure it's working, make sure it transfers as fast to all languages as possible, make sure it's small, and then keep improving, right? But definitely it's very interesting. If let's say people in the class just care about solving for cloud side applications or don't have limitations, you can go and explore all those approaches, right? So that brings us to, well, we have these different variations, right, of our models. We have words versus characters versus words and characters. By the way, if you just use characters only, performance is really bad. I didn't even list it here. But let's say you can test, like, should I be bothering implementing word and character information and figuring out how to model that, or just stick to words? What happens if I do this partitioning? Because if you remember, like we split the space and we had different random seeds going for the characters and also for the word, or should I just not care and collide everything, right? And these are just what we call them ablation studies, right? Because we want to have a good answer, like which way should we proceed moving forward, right? And here's something very interesting, right? If you take a look consistently, right, and we go into the partition SGNN, well, consistently, as we kept evaluating on different data sets, word and character was doing better, right? So we were like, okay, this is fantastic. We know that was the right thing to do. If you go to the non-partition space, let's say you don't want to bother with partitioning spaces, you just want to keep it as simple as possible. You see, well, hey, it's not bad, right? It's still word and character is doing better than words, right? But when you take comparatively and you start seeing like, should I partition or not? The answer is yes, partition, because it's doing better. And then even if I have it for words and I don't want to bother character, the answer always is yes, please partition. Then if you say, well, across all these different variations, which way do I go? And the answer is like, well, if you're going multilingual, right, especially, then go with words and characters, right? And in some of the tasks, like we got like 10% boost, right? So think about it at the bottom, non-partition SGNN with a word is almost the same like the original SGNN, right? So you start having like 10% improvement. And that happens consistently, data over data, language over language, right? And one of the things was, so I didn't, oh yeah, great. I actually have it here. But my point is like, now that you know the intuition, so what we started doing is use those intuitions and learning on the small, like somebody asked me about the documents, right? If I want to take these models, put it on long text, what do I do? So that's why we did some of these studies on smaller text, such that we know what was there, take it now, make it work for larger text, right? We have different architectures, but that's the premise of how we start and how we build on top of things. So now let's go to the interesting part. Remember, when I showed you the first slide, I said that our technology is customizable. You come and you say, this is the problem I have. This is how I want to customize. Let's say I'm building for a mobile phone. I have 2.5 megabytes, fantastic. We can customize model for you. Someone comes and says, oh, I have a watch. This is my space, like 7 kilobytes. What can you do, right? So this is what this graph is trying to answer, right? On the y-axis, we have accuracy. Here we measure accuracy because of the classification tasks, right? So you might have different metrics you're optimizing, right? In this case, it's accuracy and it's a flight prediction problem, right? When somebody tells you, can I make a reservation from LA to SF? We know that the person wants a reservation and we have to pull out that portal, right? So let's take a look at the model that is on the top, like where the number of function t is 160 and our d dimension is 14, right? So when we use this kind of configuration for the projections, we end up with 2.5 megabit model. And the accuracy of this model is 94. So it's like super impressive, like small, compact, yet so efficient. And then let's go all the way down to people who might have more like space constraints, right? And they want like 100 kilobit models. If you see for 100 kilobit models, performance drops down to 82, right? You have 10% drop in performance, but you went from 2.5 megabits to just 100 kilobytes, right? So that's very impressive. And also, as I said, what's impressive is how you can customize based on your needs those solutions, right? So there are folks that actually need even smaller space than 100 kilobits, right? Based on the application, or if you think somebody might want to have multiple different models running around, so you need to make sure you have space for all of them, right? And we did a quantization, right? So everything you see with the Q at the front, that means it's a quantized version of the original algorithm, right? With quantization, we actually get even further reduction. And in some cases, we maintain the same accuracy. Like if you remember in the first config, like the 107 qubits, our accuracy was 82. So when we quantize the same model to 33 kilobytes, like we have 80% accuracy. So 2% drop in accuracy, but if you see the model shrunk to so like magnitude times, right? And then we can even keep shrinking the models. I mean, the point here is like, how you say, based on the need, we can do that and adjust, but the accuracy actually is pretty high, pretty satisfactory. And that's the key takeaway messages, right? So what's the three things that you should remember, whether it's SGNN or SGNN++, like these models are super small, they're highly accurate, they're very fast, and they adapt to languages equally fast, right? So they can work for any of them. But one thing that's very important is, okay, we know that they satisfy these properties, but we actually always want to know in real time, well, how well do they work, right? So in our case, we actually measure the latency of SGNN on a pixel phone. You can measure on anything, but we have 3 pixel phones and you can test them for all kinds of things. And the way that you set it up is like you pass a text and you measure the inference time, right? Because you want to know in real time, how well does that work? So we take the whole 80s dialog data set, we quickly run it through our model, we average the accuracy, we average the latency. So you see like 93% accuracy, and predictions on average happen at 3.3 milliseconds, right? So these models are super fast, right? And that's the beauty of them. And let me see, yeah, just to summarize before I move to the next one, very, very important. When we started, nobody knew how to do that. We opened brand new like direction. And nowadays, by the way, we're organizing like one of the biggest workshops happening both in ICML, which is like the machine learning conferences, as well as the NLP conferences, that is focused exactly on how one builds efficient models, right? Whether it's on device, whether it's on cloud. It's a hot topic, it's very hard, but that's the beauty of, how to say, of the field, right? That you have to go and solve hard problems. And the networks that we introduced were very new. And we kept building on that. So by now you see many more variations, right? Which is normal, and it's actually pretty good. And as you saw, the whole computation of all this feature extraction and projection is dynamic. It happens on the fly, and you get rid of all the embeddings, right? So I want to spend some time, I know we have 10 minutes, but I want to spend some time just talking about the different sets of tasks that are more like structured predictions, like entities and slots. I would like to take like one question and then move to the next one.
Any questions so far? Okay, go ahead. We're good.
Fantastic. Awesome. So if you remember the example, right? We were entering in the room, talking to our device and saying, turn on my living room light, right? In all the way until here, we saw like how we predict intents, which means we wanted to know that this had to do something with issuing a command of like turn on lights, right? But even if you recognize it, actually, you cannot, like the system cannot complete the command because it doesn't understand which light exactly am I turning and where, right? And so the things that you see in blue and in red, the living room, this is actually the location where the lamp is located, and light is the object that has to be, let's say, lit, right? And to be able to extract them, well, you need the different sets of algorithms, right? We call them like structured prediction algorithms. Specifically in the setting of conversational AI, those are called like slot extractions. Each word has a label. In other cases, like similar setup is just for entity recognition and so on and so forth. And what's core now that you know like how some of these, how do you say, projections work, and that you know like how the layers work, you remember always we start from the input word, and the first thing we do is like the so-called projections. So by now you know them by heart. You decide whether you do word or characters or you want to do something more complicated, right? But as we were talking, so here, like we start modifying a little bit how these projections look like, right? And so we started incorporating, we call them conditioning operators. And they're different, like you can use dense product, you can use Hadamard product, it's up to you. And the whole idea is like we want to put those operators on top of the projection for the main reason that we want to ensure that for the same input, maybe we can use different projections, yes, that could be used for different tasks. And this is where I was saying, you either have multiple tasks and you try to build different models, right? Or you can actually be smart and maybe at input time, when you construct your projections, you can use these conditioning operators to, let's say, for 2 or more different tasks, right? And like that, use the same representations to solve more problems, right? And next, what we do is like we actually see a lot of power in terms of like using these like convolution characters, right? So we take the projection layer, we pass it through CNN, and then you can think about, you can create like different representations. When I say word like embeddings, in reality, they're all like projection embeddings of all the different layers that you have seen so far. And then because we are solving this like structured prediction problem, a very common way of doing that is by using these recurrent neural networks, right? And LSTM is a very, very common way. And the idea is like the way that words, how to say, supersede each other informs a lot about like how you make the predictions. For any type of structured prediction, these bidirectional LSTMs are very standard. So you go from left to right to get the representation of the string, and then from right to left to get the other side. And when you concatenate the two, you create these like H1 vectors that actually help you build a much better and stronger representation that is needed for the structured prediction. It's not necessary, but it's very common. If you look at all the transformer papers, right? People use attention to pick like which are some of these like things to attend over. And then because this is a structured prediction, very, very standard thing to do is like we use conditional random field models, right? To capture this labeled structure. So if you see over the years, right, we have evolved both in terms like what we do with our projection space, how we start modifying it to be used for not one, but more than one task, how you can reuse like different information, stack it on top of each other. You can make your neural networks much more complex, right? And suddenly start solving very complex tasks like structure prediction, which in 2018, when you say to someone, they're like, wow, first solve a simple problem, then go and try to solve this complicated task, right? So what's interesting is we just 2021, literally a couple of months ago, we had SIGDIAL where we presented this work, right? So people typically solve these on-device problems, as I say, for cloud server-side applications, but not for on-device. So that's like the first version of how you do that for on-device, right? Compared to where we were in 2018 to now, we've significantly like progressed. Now with these different models, you can start doing the full-fledged conversational AI, because now you can sit down and detect how your intents look like. Now you can start extracting all your slots, and practically now, not just have a chit chat system, but you can start having like a more deeper like understanding system, like what you have in Alexa, what you have in Google Assistant, what you have in Siri, right? Always we keep our models embedding free, right? And the best part, as I say, which was not clear, would it generalize to complex tasks and to these longer sequences, which also somebody asked me at the beginning. Now the answer is yes. If you do this type of models, if you structure it that way, you can model anything, right? So here's how this task looks like. So if you see, it was not like before. Before it's like, I want to fly from Boston, blah, blah, blah. And the intent will be like, oh, like, I don't know, travel request, right? Here it becomes challenging because for every word or phrase, first you need to detect that's a phrase, you have to assign a label, right? So when you say, I want to fly from Boston to Boston, you have to attach a label that says from location, city name, yes. And then when you see Denver, the model should decide that this is like to location, city name. It will detect when is the depart time, when is the arrive time, when is the morning, right? Think about it, it's very complex for any like ML system to start making differences between different location types and their property, right? Boston and Denver are cities, but one is from destination, the other one is to destination. You have two ways to say time, right? One is departing, one is arriving. And typically we call this kind of structure prediction problems very complex, right? Hard to solve. There are certain tasks we the NLP community are very good, and others like conversational AI, where the slot names, right, which is these labels that you see, just explodes. It becomes really challenging, and sometimes it's even overlapping, right? But today, the good news is we can solve such type of models. Also, what's interesting is because the whole community, NLP community, picked up and started trying to build these different efficient models, now technically we can start comparing against some of them, right? So we took all of the different methods that were developed in the literature, from the attention, RNNs. Some people are doing this capsule neural networks that became very popular 2019, BERT, which is like widely used, the distilled version of BERT, which is small and compact, right? And we run them through both AGIS and SNPs. They're both data sets that are on conversational AI. If you see an arrow, that means that we're doing like better than them. And if you see consistently, the models are doing better, right? In some cases, it kind of is on par to them, right? But it's a good news that our technology keeps evolving. It continues to improve state of the art. And we're still like very small and compact, right? So if I double click on people who did specifically in 2020, like the latest work that was done for all of these like on-device models, right? And Desai is especially like looking into that, and he's doing different things. He's taking convolution, compressing convolutions with different models and doing like structured pruning and pruning the network and pruning the outputs, right? We consistently improve those models, right? And what you're going to learn from industry, like sometimes if you just prune or if you just compress models, that does not necessarily mean you're going to get better model, right? So that's why I was saying, learn to model correctly, like your features, learn to like, how I say, strategize how you want to do, think about what's the right neural network, then try them, learn from your mistakes and iterate, right? So here's like a very nice graph that shows you a comparison between BERT, smaller version, only 110 million parameters, the stillbird, and then our SODA, we call it SODA, our approach, right, with very lightweight, like 800K parameters. So smaller means better, right, which means with a smaller model size, you can go and hit the same performance. So if you take and compare, for instance, the stillbird, 66 million, we are like SODA 800K, right? This is between 100 and 1,000 times smaller model, right? And we're still like achieving better performance. And we actually, it's very similar performance to the 110 billion parameter model of BERT, right? So that shows you, as somebody asked me earlier in the class, can I throw these like bulky like embeddings? The answer is yes, you can. And then somebody else asked me, well, can I solve long documents? The answer is yes. And can I solve complex structure prediction tasks? The answer is yes. So there's a lot of promise. And I think soon people are going to start using all these models like on their devices. And in some cases, they might be already out and out there. So we do different ablation studies, and this is always the case. So everything we do, like both Sujit and I, are very meticulous. We want to make sure we understand what's going on under the hood, right? I showed you that we have two of these different conditioning operators, right? The Hadamard and the dense. If you see, yeah, sure, the dense is slightly better, but they don't like drastically impact your performance, right? But then if you ask me, like, should I use convolutions, like just like I showed you that we had them on our model, or should I just drop them? Actually, we do see that if you do the convolutions, it's actually working way better, right? So definitely that's a way to go. And then the last layer, because it's a structured prediction model, right? The question is like, well, do I want for every like token to make like a multi-class prediction? Or do I want to just use a CRF that will capture the boundaries and assign the label? So if you see, there's like a 2-3% difference, right? So CRFs are slightly slower to train. But I think if you increase the label space, right, and you want to deal with something like 100 to thousands of labels, then I think CRF works better, because definitely we have in industry as well as in academia a lot of signals that this is the case, right? And almost getting there. So training time for the whole task. And actually, do you know, some people said, oh, good, you're training on cloud. Well, think about it, you can train on anything, right? Typically in production, you can train on cloud because you have lots of data, and the goal is like make a smaller model and push it out. But let's say if you're doing like your own like project, right? For like, I don't know, at Wade's next class, which there is a project there, right? So you can actually do it on your computer. You don't even need a GPU. So that's the good news. You can actually build your models on CPU. And we specifically, for people who ask us that, we sat down, we showed them it's very efficient. You can train them very quickly. You can keep iterating, right? But what's important is like in test time and inference, definitely based on whether you do it for phone or you do it for watch, make sure, right, that you compare. It's just kind of nice to know, are these things working, right? And so our SODA algorithm on average, right, when we took all the test example is like 10 milliseconds, like super, super fast, right, for such complex tasks. So recapping this part too, it's amazing to see how far in 4 years we've gone from people who didn't believe this possible all the way to solving step by step different problems and coming to solve like one of the most challenging ones, right? Always making sure that we are embedding free, everything is dynamic, on the fly, and most importantly, that our approaches generalized to other languages, generalized to other complex tasks. And I know we're right on time. Two things I want to show to people. So we have different papers. In the papers, as I say, we're fully transparent, always use like data sets that people can download and test against. And we have different sets of papers. Some, as I say, like Performer is learning representations on the fly. The misspelling, robustness misspelling for projections. We did like attack towards the models. We want to know, like, are these models good just on text that we see, I say, nicely written, or does it also do very well on tweets and social media text, which often have misspellings, which often have emojis and all kinds of things. And then from there, you can see all of our work on like long documents and so on and so forth. And these are just some of the things. I didn't put everything. But with that, I would love to thank everyone. Yeah. And maybe what's the right way to stop projecting? Perfect.
Thank you, Doris. Also, thank you. The recording.